Hello, and welcome to another exciting episode of Astronomy Daily, your go-to podcast for all the latest and most fascinating updates from the world of space and astronomy. I'm your host, Anna, and thank you so much for joining me today. We've got a stellar lineup of stories for you, including the conclusion of NASA's NEOWISE mission, the challenges posed by China's recent satellite launch, and groundbreaking discoveries in meteor science. Plus, we'll debunk a long-standing theory about black holes formed from light and explore what these findings mean for future technological innovations. So sit back, get comfortable, and let's journey through the cosmos together. NASA's NEOWISE mission has officially come to an end after over a decade of invaluable service in detecting and studying asteroids and comets. Launched as the Wide Field Infrared Survey Explorer, or WISE, back in December 2009, the mission was initially intended to map the entire infrared sky in just 7 months. However, its capabilities proved so beneficial that it was repurposed as NEOWISE and extended to focus on identifying near-Earth objects, a crucial part of planetary defense. One of NEOWISE's most significant achievements is its comprehensive survey of the sky, producing all-sky maps that include over 1.45 million infrared measurements of more than 44,000 solar system objects. This mission alone spotted 3,000 near-Earth objects, with 215 of those being discovered for the very first time by NEOWISE. Additionally, it found 25 new comets, including the remarkable Comet C2020F3 NEOWISE, which offered a dazzling display in the summer of 2020. The decision to conclude the mission was driven by practical constraints. As solar activity increases, it causes the upper atmosphere to expand, creating drag that the NEOWISE spacecraft lacking propulsion can't overcome. This decay in orbit means that NEOWISE will eventually fall back to Earth and burn up in our atmosphere by late 2024. Despite its end, NEOWISE has left a lasting legacy. The data it collected will serve scientists for years to come, and it has paved the way for future missions like NASA's NEO Surveyor. This next-generation mission aims to continue where NEOWISE left off, enhancing our ability to detect and characterize some of the more elusive near-Earth objects. The success of NEOWISE illustrates how resourceful and resilient space missions can be, repurposing technology and maximizing output long beyond their original missions. It is a testament to the ingenuity and dedication of the teams at NASA's Jet Propulsion Laboratory and other partners who supported NEOWISE's mission over the years. As we say goodbye to this groundbreaking mission, we look forward to what's next in our quest to understand and protect our planet from potential cosmic hazards. As we look forward to the launch of NEO Surveyor, slated for no earlier than 2027, we can be assured that NEOWISE has set a solid foundation. Its exhaustive data sets and the knowledge it accrued will continue to be a cornerstone of our planetary defense strategies and our broader understanding of the solar system. All thanks to a brave little spacecraft that scanned the skies from its low Earth orbit, ensuring we keep our eyes on the interstellar ball. This past Tuesday morning saw the liftoff of a Chinese Long March 6A rocket, launching the first 18 satellites for China's ambitious Tianfan broadband network. This mega constellation network aims to host up to 14,000 satellites, promising widespread internet connectivity. However, this inaugural launch did not go as smoothly as planned and has already raised significant concerns about space sustainability. Shortly after successfully placing the satellites into low Earth orbit, a troubling event unfolded. The upper stage of the Long March 6A rocket broke apart, dispersing a cloud of debris into space. According to the United States Space Command, over 300 pieces of trackable debris have been identified, with many more smaller shards likely unaccounted for. These fragments are now racing around our planet, adding to the growing problem of space junk. This incident has set off alarms within the space community. China's Tianfan project, if each of its launches were to result in similar debris creation, poses a substantial threat to the already cluttered low Earth orbit. We must not forget the previous incident with a Long March 6 upper stage in 2022, which resulted in over 500 pieces of trackable debris. The pattern suggests that without proper mitigation, such launches could contribute immensely to space debris. Experts like Audrey Schaffer from Slingshot Aerospace underscore the importance of adhering to space debris mitigation guidelines. The fragmentation of the Long March 6A rocket serves as a stark reminder of the necessity for robust space domain awareness and sustainability practices. The growing population in Earth's orbit, which includes around 10,000 operational satellites and countless pieces of debris, demands our collective attention and action. As we look towards an increasingly interconnected and space-reliant future, ensuring sustainable practices in space operations is not just advisable, it's imperative. Did you know that not all meteors just blaze through the sky and disappear in the blink of an eye? Some actually leave behind a lingering, glowing trail. For over a century, astronomers have been intrigued by these persistent meteor trails, trying to unlock the mystery of what causes them. Recent studies have finally shed light on this captivating phenomenon. Contrary to what many might have believed, the key to these lasting trails isn't the speed or brightness of the meteor. Instead, it's all about the meteor's altitude as it enters Earth's atmosphere. Researchers found that meteors that zoom in at around 90 kilometers up are the ones most likely to leave behind a persistent afterglow. This is because at this height, a chemical reaction occurs between the vaporized metals from the meteor and the oxygen and ozone present in the atmosphere. This reaction emits heat and light, sustaining the trail for minutes or even up to an hour. It's incredible to think that these trails twist and writhe like luminous serpents, carried away by the winds high above us. The discovery overturns previous assumptions that only the fastest and brightest meteors could leave such trails. In reality, even slower meteors can produce these mesmerizing afterglows as long as they dip to the right altitude. This revelation opens up new possibilities for studying our atmosphere. Persistent meteor trails provide a rare, free opportunity to probe the elusive layers of our atmosphere that are otherwise difficult to study. So next time you spot a shooting star with a lingering glow, you'll know it's taken the perfect dive through our skies. So what do these persistent meteor trails mean for our understanding of the atmosphere? Well, it's quite fascinating. These enduring trails provide a unique window into the atmospheric chemistry at altitudes that are otherwise difficult to study. You see, the trails are formed when metals from the meteor react with atmospheric ozone, and this process emits light that can linger for minutes or even up to an hour. Because of their height at around 90 kilometers, these meteor trails form in a region that's sort of a no man's land for conventional atmospheric studies. It's too high for weather balloons to reach and too low for satellites to monitor effectively. Persistent meteor trails, however, happen more frequently than we once thought, providing almost a constant stream of natural experiments that we can observe and study. I'm particularly interested in the role these trails could play in measuring the small concentrations of ozone at such high altitudes. Since ozone plays a crucial role in absorbing ultraviolet radiation from the sun, understanding its distribution is essential for climate science and atmospheric chemistry. The new research can also help us grasp why some trails maintain their luminous forms for extended periods while others dissipate quickly. This involves delving deeper into the minute interactions between charged dust grains and the electric fields they generate, potentially leading to a new layer of detail in our atmospheric models. The implications for meteor observations are also significant. As we gather more data, we can improve our predictive models for meteor showers and better understand the various factors that influence a meteor's visibility and the persistence of its trail. In short, these findings not only solve a century-long mystery, but also open up new avenues for atmospheric and space science research. It's a rare win-win that shows how sometimes the most fleeting phenomena can offer the most enduring insights. Have you ever heard of Kugelblitze, also known as black holes created from concentrated light? For decades, this concept has fascinated astrophysicists and theoretical physicists alike. These hypothetical black holes were thought to be formed by incredibly high concentrations of electromagnetic waves, essentially intense light. Sounds intriguing, right? Well, recent research has shown that this idea, long a staple of futuristic theories, might just be a myth. A team of researchers from the University of Waterloo and Universidad Complutense de Madrid challenged the Kugelblitz theory using advanced mathematical models that include quantum effects. Their findings were groundbreaking. The light intensity required to form a Kugelblitz far exceeds anything observed in the universe. To put it simply, even the brightest and most intense light sources like quasars can't achieve the concentration needed. So why is this important? For one, it helps clarify the limitations of our understanding of black holes and the conditions necessary for their formation. Traditional black holes, formed from collapsed masses of regular matter, are well studied and understood within the framework of Einstein's theory of general relativity. The idea was that since energy curves spacetime, a high concentration of light, energy in its most radiant form, might also lead to a gravitational collapse. However, this theory did not consider quantum effects. The researchers discovered that before you could ever reach the necessary intensity of light, quantum mechanical effects would kick in. At extremely high light concentrations, particles such as electron-positron pairs would spontaneously form and scatter away, preventing the light from concentrating enough to cause a gravitational collapse. This discovery is significant not only for its immediate implications, but also for the future of scientific research. Just as the science behind PET scans was theoretical before finding practical applications, understanding these quantum limitations could pave the way for future technological innovations. It reminds us that the field of quantum mechanics holds many secrets yet to be uncovered, and each discovery takes us one step closer to deeper understanding. So, while the notion of Kugelblitze may now be debunked, the research contributes profoundly to the intersection of quantum mechanics and general relativity, two pillars of modern physics. It's a testament to how our theoretical frameworks continually evolve, driven by new findings and innovative research. As Eduardo Martin Martinez and his team continue their groundbreaking work, we can look forward to a future where today's theories become tomorrow's technological cornerstones, shaping the way we understand and interact with our universe. Thank you for joining us on this journey through the latest in space and astronomy news. I hope you found today's stories as fascinating as I did. I'm Anna, and it's been a pleasure to bring you the details and implications of these incredible events and discoveries. Remember, if you want to stay updated with all the latest space and astronomy news, head over to our website at astronomydaily.io. There, you can sign up for our free daily newsletter and check out our constantly updating newsfeed. We've also got all our back episodes available if you want to catch up or revisit some of our favorite topics. Don't forget to follow us on social media. You can find us under Astro Daily Pod on Facebook, X, YouTube, and TikTok. We love engaging with our community, so be sure to drop us a message or comment on your favorite platform. Until next time, keep looking up and continue exploring the wonders of the universe with us. Thanks again for listening to Astronomy Daily.